So glad there's only like 5 weeks of classes left. Especially for all of you who are like thrust into teaching right away. Oh, baptism of fire. Okay. Now, a quick comment about notes from last time. That unfortunately, I apologize for rushing things a bit toward the end. So what I did after y'all left. Oh, I knew there was something I wanted to ask you all. How many of you, like when I'm going through and covering something and then typing these things up, how many of you are like actually taking notes? Okay. Yeah, I'll just. Oh, okay. I see, Caitlin, you raised your hand too. How high tech of you. So, okay, I was just curious about that. So, all right, that means that what I'm doing now is more important because what you actually would have taken notes from on Wednesday. So I don't know if you also go back and look at the like PDF that I post, but I would highly recommend doing that this time because after class I went back and I filled in more things actually like toward the end about like all these things because I was going through certain things in the book as I recall, and so I filled in more details here that you might not have in your notes. This is going to be especially important for two of the homework problems from that section because there's this one theorem that's a if and only if to be proven, and it's broken down into two problems for proving each half of the if and only if. So there's some detailed hintage here that you should certainly follow. Now, as far as homework goes, I guess I just saw some homeworks have been turned in. There's a bit of a lag between when I cover something and the assignment being due. Like, what section are you all on now as far as homework goes? Like,
I'm on 7.6.
Oh, okay. So you're approaching the very end of chapter 7. Okay, so then after you finish that, okay, then you'll be getting to this orthogonal polynomial stuff. So I think, which is about like next week. So there should be time during class next week, and maybe also Wednesday for 7.6. So certainly homework questions are always welcome, and it's a good idea to have your questions asked here so that everybody can benefit. So whatever was not covered as thoroughly or slowly as ideally it probably should have been, we can fill in gaps that way. But if you don't already, I would urge you to, especially for this 8.2, take some time, look through a PDF, supplement your notes, your handwritten notes as needed, because usually after class is done, I just take that exactly what I typed out and I post that. But here I went back and it took a fair amount of time to add a lot of things. So I just don't want y'all missing anything. Okay. And actually, once you do the 7.6 homework, that should help set the stage for certain tidbits of 8.2 also. Okay, now so now we go into chapter 9, the last chapter that I'll be covering, but I'll be covering a fair amount of it during the rest of the semester. So this one section, it's on numerical differentiation, and then the rest of it's going to be numerical integration. Okay. So So the problem we're going to take on here, whoops. Oh, I put that in the wrong place. Oh, yeah, I again put it in the wrong place. Okay, jeez. This is going to be interesting. Let's see. My brain is, I'm not sure where it is right now. So the problem we're taking on is, given values of function f of x at select points, and this is going to be rather strange notation, but I'll explain it shortly. So I have a bunch of x values that have indices that are positive, negative, or 0. So if we have values of f of x only at these points, so we don't necessarily have a formula for f of x, we only have these data points. So it's like an interpolation problem where you're given x and y values to work with. So we're trying to find an approximation of a derivative at the select point x naught. And the approximation would have this form. Okay. Okay. So in other words, we're going to take a linear combination of whatever f values we have, with a certain coefficients, these c's here, all of that divided by, this is what I get for winging it. I jumped the gun here. I'll just delete that part. Okay. Okay, so we want to find coefficients to multiply these f values by, so that the result is an approximation derivative. And I say approximation, so there's going to be some error here, but we want the error to be as small as possible. Now to explain my indexing here, so if we have a negative index, or less than x naught, and if they have positive indices, are greater than x naught. So that's why I indexing scheme. So we could use points on, and the limits j and k, they can be anything. If they're not necessarily equal, we might not have any points to the left of x naught, or so we'll see some approximation schemes like that. So we want to try to use these function values to approximate the derivative as accurately as possible. Okay. Now we get an idea as to how to approximate the derivative just by going to the definition. There are different ways of writing definition. I'll use this one. That is a limit as h goes to 0, and let's dust off your calculus 1 knowledge. What's supposed to go here? Who remembers?
I guess it's not. Or is it honestly? Yeah, okay. And then plus f of x naught. Or is it minus there? Okay, minus f of x naught all over h.
Yeah.
Okay.
You know, and actually, this will become relevant later. Because here, if we assume that h is positive, we're using f value from a point to the right of x naught. But if I were to replace h by minus h throughout, and simplify as much as possible, I could also write it this way. Okay. So here I'm using a value of f at a point to the left of x naught. So it works out either way. Now that's, and it has to be a minus because this is something where, as if you simply plugged in h equals 0, you get 0 over 0. Okay. So the exact value of a derivative comes from the limits as h goes to 0. So by choosing a specific, an actual number, then what we could do is we can approximate the derivative because, and naturally, the smaller h is, presumably, the more accurate the approximation will be. But if we do that, how accurate is such an approximation? I mean, so we could use this definition and justify approximating a derivative a certain way, but we'd like to have some concrete idea as to the error. Just like with polynomial interpolation, we have an error formula, and like also for certain spline interpolants too. So we like the same kind of thing. And in fact, what we saw in interpolation is eventually going to help us with that. But what I'm going to do today is focus on a different way of obtaining an approximation. Is something that has come up in the homework. Taylor polynomials. Okay, so what I could do is if I use Taylor's theorem, I have f of x naught plus h. So I want the value of this by Taylor expansion with x naught as the center. Then what I would get is f of x plus x naught plus h is f of x naught plus h f prime of x naught. And then the next term, I could do the next term in a Taylor expansion. Keep going, but if I let this go to infinity, that would be a Taylor series. But I actually don't want a Taylor series. I want to stop it at a certain point when I have a finite number of terms in Taylor polynomial. So I'm actually going to stop right here, and instead of just having a next term, what I really have is a remainder term where f double prime, which the Taylor remainder is almost exactly the same as the next term in the Taylor series, except the derivative is not evaluated at x naught; it's evaluated at the at some unknown point. So if we assume that h is positive, actually it can't be 100% certain it's the open interval, so I'll go with the closed interval. So sorry, that's not x naught. That's supposed to be squiggly, also known as a Greek letter xi. Lies in between the center of the expansion and the point of evaluation, x naught plus h. So now I'll just rearrange this. If I rearrange this to get f prime of x naught isolated on one side, then I'll have something very closely resembles the definition of a derivative. All right, so I would actually get exactly what the definition would give us, except without the limit here. And then this term gets moved to the other side and divided by h. So now here we have our approximation for whatever h we've chosen, and then here is the error. So we do have an error formula in this case. So this is called forward difference approximation. And because the error is big O of h, meaning the order of magnitude of the error is h to the first power, we say this is first order accurate. Right. And I say blah there because that's definitely nothing to be excited about. It's definitely not super accurate. And it'll do. It is useful in certain cases, especially when the function is badly behaved. But yeah, it's definitely nothing to be excited about. All right. So questions to this point?
I do have a question.
Yeah.
So why did we stop in this specific Taylor polynomial at the second derivative?
Oh,
you kind of blinked out for a minute, so you might have said something, but it quieted out for a minute.
Oh, actually, I think I really did not explain why. But I appreciate you offering me the out. So the reason why is since I'm only using these two f values, I could have continued. However, all that would do is it would not change the approximation at all. It would give me a different form for the error term. So what I would have is minus h over 2 f double prime at x naught plus however many more terms I would have wanted. That would have higher powers of h, higher order derivatives of f. It would give me no really useful information about the error. So that's why. Generally, we want to have like as condensed an error formula as possible.
Okay, thank you. And then I guess that being said, it would always be, if I know you said it wouldn't give any significant difference, but the error is always going to be on the last term.
Yeah, so basically you have your exact value f prime of x naught will be equal to your approximation plus whatever else is there is the error.
Okay.
And so here we're taking a linear combination of two values of f. Your coefficients are 1 over h and minus 1 over h. So that would be the c's right here. So in this approximation, we have c1 is equal to 1 over h. So minus 1 or c0 is equal to minus 1 over h. And that's it. Those are the only two. You only have two values of f that we're using here. Notice the coefficients sum to 0. That's actually going to be true for every single approximation we come up with. Okay, and in fact, I can explain why it ought to be that way right now. Because suppose f is a constant function. Then what would I have here? I could pull this f of xi outside the sum because every value of f will be the same from it being constant. So what my approximation is just the sum of a coefficients. Well, the derivative of a constant is 0. This has to be 0. Therefore, the sum of the coefficients has to be 0. So that's why. So to get the derivative of a constant function right, we need that. Because I mean, if it can't get a constant function right, then it's not a very useful approximation. Okay. So this is simplest approximation. Now, if I were to do the same thing, Taylor expansion, but now I'm expanding f of x naught minus h. Well, really, it's going to give me almost exactly, really the exact same thing, except throughout we replace h by minus h, as I mentioned earlier. And because of that negation, the error term will also be the same except negated. Okay. All right. So now let's make things a little more interesting. If I do Taylor expansions of both points, x naught plus h, f of x naught minus h. So what we have here is f of x naught plus f prime, or h f prime of x naught plus h squared over 2. And this time I'm going to go out a little further. Is there a technical issue here? Oh. Yeah, I see all of you are frozen too. Dang it. There's just a little movement. Are you able to hear me?
It's in and out.
Yeah, like you're really grainy. Okay, well, that video quality improved a little bit. Is it still? I haven't done anything new in the video on my screen, but hopefully that was just a momentary hiccup. Okay. Oh yeah, because right now on my screen, I guess you're seeing what's on my screen right now because I'm sharing the whole thing, and yeah, since Chelsea's on campus, as am I, so you're coming in super clear on my video, and Walker was not. So it was the contrast there was kind of funny. Okay, I'm taking a look at the chat here. Okay. All right. So apparently we're all suffering. So let's just see. I'll attempt to keep going here and see what happens. So all I'm doing is Taylor expanding f of x naught plus h, and I'm going to go a little further than I did before. So this will be the last term here. So h cubed over 3 factorial, which is 6, at f triple prime at some unknown point. Then I'll call it C1. And then I'll have the same kind of expansion for f of x naught minus h. Okay, so here I'll have a minus. So really replacing h by minus h throughout. The terms involving f double prime will be the same because you're squaring the h. Okay, this will be a minus. And then the unknown point will be different because C1 is between x0 and x0 plus h. C2 is between x0 and x0 minus h. Okay. Let's see, I'm going to need to move this to a new page. I said new page. Okay. So what I'm going to do now is I'm going to subtract these two. Now, when I subtract these two equations, so I have f of x naught plus h minus f of x naught minus h, these terms will cancel. These terms will cancel. These terms will add together because they're already of opposite signs. So I can have 2h f prime of x naught. So what I will get is f prime at x naught is equal to f of x naught plus h minus f of x naught minus h all over 2h minus h cubed over. Now it's gonna seem strange. I'm gonna write h cubed over 12, but you'll see why in a moment. Oh wait, actually this should be a 3. Went the wrong way there. All right. So what will happen is these two terms also add together, but then you divide by 2h. I was actually giving me h squared over 12, and then I pull out a factor of 2 here. So I'm sorry, this should be a 6. I'm going to, whoops. Ah, dang it. Sorry about that. You just saw someone's recommendation letter you weren't supposed to see, but whatever. Okay. Sorry, this is what I get for winging it. Okay. All right. All right. So what we have here is correct. So all I did with here was I subtracted these two equations. So second equation subtracted from the first. Divide by 2h to isolate f prime by itself. And then these error terms had to be moved to the other side. Thus the minus here. And then I broke up the denominator like this. So here I have this approximation of the derivative, which you could also think of as, if I were to take this approximation and this one and add them together, and divide by 2, so I'm taking the average of these two. And I just realized I totally made a mistake in this one. The backward difference is supposed to be that. Okay, I'll make sure I had it correct up above. Yeah, I did. Okay, if I add these two together and divide by 2, so I average them, the f of x naught terms cancel out. And I would get exactly what I have down below. But if I take the average of these two, based on what you see written here, what happens to the error? Because here we have the error term for forward difference, here it is for backward difference. If I add these two equations and then divide by 2 to get another approximation of f prime, what's up with these errors?
Would the errors
The audio dropped out at the worst possible time.
Wouldn't the errors disappear?
You'd think so, and in a sense they do, because if I were to, now here I stopped the Taylor expansion at this term. If I had gone an additional term, I could have said h squared over 2 f double prime at x naught plus more terms, for both a forward and backward difference, and those would have canceled. So now xc is a unknown point in this interval. For the backward difference, xc is in, whoops, in this interval. So these points are different, even though I've given them the same variable name. So they do not literally cancel. But what you could say is that, so even though the errors don't cancel entirely, the leading order error, the part that is of order h, does cancel. And that's what we see here. Because when I subtract these Taylor expansions, these terms that give rise to the error in the previous approximations, they really do cancel. And then we have this. So what were like secondary error terms in the forward and backward difference now move to the forefront and become the leading error terms. So that's what we have here. And notice the error is proportional to h squared now. And we call this the centered difference. And that is second order accurate. So what does it mean to be second order accurate? The error is proportional to h squared, meaning that if I reduce h by a factor of 10, then the error will be reduced by a factor of roughly 100. So the error goes to 0 a whole lot more rapidly than when it's first order. Now this is a rather cumbersome error term, but I can actually clean it up a bit. If we know that f double prime is continuous on the interval x naught minus h, x naught plus h, then I can write the error approximation this way. Where we just have a single unknown point and not dividing by 2. Okay. I'll bet the name intermediate value theorem rings a bell, but you might not remember what it said. So I'll jog your memory a bit. So the intermediate value theorem, or IVT, states that if f is continuous on an interval AB, then on the open interval AB, f assumes every value between f of A and f of B. So, in other words, there's some point, unknown, in this interval, like where f is equal to any number that falls between the values at the endpoints. So how did I use that up here? Well, the average of these two values, f triple prime of xc1, oh, actually, it should say if f triple prime is continuous. That's the assumption I need. Okay. So if I look at these two function values, f triple prime xc1, f triple prime xc2, if f triple prime is continuous, then the average of those two falls in between, because the average of two numbers always falls in between the two numbers. Therefore, there's some x value between these points, and therefore certainly in this interval, where f triple prime is equal to this average. So that's what justifies me doing this right here. So questions about the centered difference. Now, the next approximation I'll try to come up with is here. This one requires knowledge about f to the left of x naught and to the right of x naught. Whereas both of these approximations are one-sided. You only need information about f either to the left or to the right of x naught. Well, what if it's all you have? Like, what if you have information about f on an interval, and you want the derivative at, say, the left endpoint of the interval? So you don't know anything about f values to the left of x naught, only to the right. So, but I want more accuracy. Like, suppose I don't want to use this first order accurate crummy forward difference. I'd like to use more points to get second order accuracy again. So here's what I can do. Okay, so I'll make this a new section. Right. I need to break this up a little bit. All right. So how to do higher order approximations? How can I approximate f prime of x naught at more points? So far, we've only used 2 points. In order to get higher order accuracy. So I'm going to give a general form of the approximation. So we assume that f is known at selected points to the left or right of x naught, where each of these points is equal to x naught plus IH. Okay. So I wasn't really assuming equal spacing before, but now I am for convenience. So now we're going to use that assumption of equal spacing to get an approximation of this form. F prime of x naught equals 1 over h All right. Actually, I was filling what xi is, x naught plus IH. So in this case, we've seen from previous approximations that whatever coefficients we get, there's always a factor of 1 over h in them. So now that I'm assuming equal spacing, I'm just going to put a 1 over h factor in the form of my approximation because I know it's going to be there anyway. And so then these CIs will be specific numbers. They won't depend on h. I actually wanted, you saw I typed that 1 over h factor earlier, but when I was up here, I couldn't do that yet because at this point I was not assuming equal spacing. So it didn't make sense then, but now it does. And I can't forget my error term. Okay. So what I'm going to do to figure out what these coefficients should be is I'm going to replace each of these, f of x naught plus IH, with a Taylor polynomial. Now what I'm going to do is I'm going to let n equal j plus k. Right. So we have a grand total of n plus 1 points that we're using for this approximation, including x naught that falls in between here. So we're going to use a Taylor polynomial, degree n, with remainder. The remainder will help us with the error. So then I'll just substitute that in here. So it's going to get a little messy. All right. So I'll have my I'll have a sum. Let's see. I need to use another letter. Okay. I'm using I, J, and K already. Now this notation, f to the with a superscript of p in parentheses, that means p derivative. Right, so that's a concise way to refer to higher order derivatives over p factorial. And then it's this x naught plus IH minus x naught, and that's being raised to the p power. So that's just going to be I times h raised to the p power. So this is my Taylor polynomial approximation up to degree n. And then I have to include the remainder term, which will help me with my error. So that'd be f n plus first derivative. Okay. Okay, evaluated at an unknown point, which I'll call Ci. It's different. Each of the Taylor polynomials is independent, so it has its own remainder unknown point. And then I have n plus 1 factorial. So, and then we also have IH to the n plus 1. So it's just like the next term in a Taylor approximation, just evaluating a derivative at an unknown point rather than at x naught. So this is what I get from all of that. Okay. Now I need to find a way to obtain these coefficients, these CIs. So what I will do is I want to separate this into two parts, one for the approximation, one for the error. So everything that's outside the big square brackets, I'm going to copy that and move it inside. Okay. Okay. And now, so what we have here, this part is where my approximation is going to come from, pretty much. And then everything else here is going to help me sort out my error. So really, what's going to happen is the error is going to turn out to be minus all of this. Okay. So the idea is we want to make this equal, we'll find the coefficient Ci if I make all of this equal to f prime of x naught. So to figure out how to do that, I'm going to interchange the order of these summations. Okay, so I'm going to move this to the outside. Okay. And then anything in here that does not depend on I, I'm allowed to pull out. Okay, so for instance, this fraction I can certainly pull out. And then if you get I to the P, that has to be left in here. But the H to the P can be pulled out. Whoops, I to the P. Okay. So now if I take a look at this inner summation right here, because I want this whole expression to condense to just f prime of x naught. So the way I can do that is if p is equal to 1, then this is just going to be h, which will cancel out with this h. If p is 1, then this factorial is 1. So everything that's outside here, if p is equal to 1, this is f prime of x naught. So therefore, I want sum I goes minus to k of ci times I to the first power. I want it to equal to 1. So that's one equation that these coefficients have to satisfy. Otherwise, I want this summation, this inner sum, I want it to be 0. That way, if all of these conditions are satisfied, then this will collapse to f prime of x naught. So then I'll have the coefficients that give you an approximation, and this part right here would end up being the error. Okay. So we have n plus 1 linear equations in the n plus 1 unknowns. That will give you a way of a differentiation rule, a numerical differentiation rule. Questions about this? I'm going to show an example of this approach. So what we want to do is approximate f prime at x naught using these values, f of x naught itself, f of x naught plus h, and f of x naught plus 2h. So those 3 points. So therefore, j is equal to 0. I have no points to the left of x naught. And then k is equal to 2. That's the largest positive index that we have. So if I take what I have before, and bring it down here, but now I'm going to set n is equal to j plus k, which is equal to 2. Okay. I goes from 0 to 2. Okay, and then all right. Oh, and then wherever I see n, I can set that equal to 2 also. So that'd be f triple prime. At unknown points over 2 plus 1 free factorial, which is 6. And then I have IH. Or really, I'd have I cubed, H cubed, H cubed. But I have this 1 over H sitting out here. So I can get rid of that. And then I'd have H squared. So my error, whatever it's going to turn out to be, will be order H squared. Now, what about the system of equations that I have? My coefficients I'm looking for, C0, C1, C2. Whoops. Satisfy these three equations. If I go back up here, if P is 0, then I just have a sum of the coefficients. Must be 0. I mentioned that before. So that's my first equation. Then I have coefficients times I equals 0, 1, 2 raised to the first power. So that's going to give me C1 plus 2C2, and that is equal to 1. For a P equals 1 case. And then for P equals 2, I'm going to have I equals 0, 1, 2 raised to the second power. So I'll have C1 plus 4C2, and that is equal to 0. So this system of three equations, these three unknowns, comes from these conditions right here. So one of the homework problems is writing MATLAB code that will set up this system of equations for a general case, for whatever value of however many points that you have, and whatever indices minus j to k that you have, to solve for the coefficients. Basically generating a numerical differentiation scheme. So what do we get for the solution? So we actually get, okay, so we have, all right. So I'm going to make sure to not get my differentiation rules mixed up, but okay. Minus 2C2 is equal to 1. So C2 is equal to minus 1/2, and then C1 is equal to, okay, so it's 2, and then the coefficients have to sum to 0. So C0 is equal to minus 3/2. And I I'm going to cheat and make sure that was right. Whoa, stop. Okay, yes is right. Okay. So now if we incorporate these coefficients, I need to go back up here. This is view of my approximation. So f prime at x naught is equal to. All right, so I have minus 3 f of x naught, okay, plus 4 f of x naught plus h minus f of x naught plus 2h. So just by putting these coefficients in here and having everything over a common denominator, and then everything else. So what we have from here is the error. So that's going to come from this formula here. So if I plug it, let I go from 0 to 2. When I is 0, I have 0 cubed, so I get no contribution there. And remember, so what's going to happen is the error is going to be the negative of this. So I'm going to have minus C1. So it's going to put all the error terms together from here. F triple prime of C1 over 6. 1 cubed, but that's 1, and that's going to be h squared. And then I'm going to have C2. Okay, so and I'm going to have another expression of this form, f triple prime of C2, also over 6. 2 cubed, which is 8, h squared. Okay, so now I need to deal with all these numbers here and simplify those as much as possible. So I'll have over 3, and then over here I'm going to have 8 over 12, so 2/3. So if I try to simplify this as much as I can, sorry, there's a bit of a mess that I'm going to clean up. Okay. Okay. So what we have here is the error. The important thing here is that it's order h squared, so it's second order accurate, just like the center difference was. And it depends on the third derivative, also like the error in the center difference was. All right, so any questions about what happened here? Now, what I would like to do is combine these into one term like I did for center difference using the intermediate value theorem. The problem is, because of a minus here, we cannot be absolutely certain that this value really is intermediate to f triple prime x(c)(1), f triple prime x(c)(2). So I cannot use the intermediate value theorem to justify, like for instance, taking this minus 2 times this and combining it into one term. Although if I did do that, it actually would give me the correct error formula. I just can't use the intermediate value theorem to justify it. On Wednesday, I'm going to show you a very, very different approach to deriving these numerical differentiation methods that involves Lagrange polynomials, and then the error formula can be obtained by using the error formula for Lagrange interpolation, which is actually one of the main reasons why I covered Lagrange polynomials in the first place, because of the usefulness that it has for numerical differentiation and integration. But we also have a Taylor series approach that's basically the way to generalize using the definition of a derivative in order to approximate a derivative. So you can use Taylor expansions at whatever points you choose and get a system of equations like this for the coefficients, so that your approximation that's of this form can approximate the derivative as accurately as possible. One thing to point out is this approach to approximating f prime of x naught is exact for all polynomials of degree n or less. And the reason why we can see that is if we go to what we have here, like here's our, so this condenses to f prime of x naught, and therefore this is the error. Notice the error depends on the n plus first derivative of your function. So if f is a polynomial of degree n or less, this derivative is 0. So the error will be 0 in that case. Right. So you can see how it can be beneficial to use more points. You get a higher power of h in the error. Its degree is it's exact for a higher degree of polynomial, but for functions that aren't polynomials, you're involving higher order derivatives, and those can be very badly behaved. So it's not all roses. You may run into trouble from using too many points, which is why in some applications where you're dealing with functions that are oscillatory, it may actually be better to use a low degree rule, something as simple as a forward or backward difference. So even though those approximations seem very simplistic, they're still needed in certain situations. So that's why it's important to understand in your error formula, a lot of people focus on the power of h, saying, okay, that determines the order of accuracy. But this part matters too. You need to have an understanding about all parts of the error formula to be able to use these kind of approximations, use the right one for different situations. All right. So I think that's all I could possibly get through. We're almost out of time anyway. So Taylor polynomials is one way to figure out how to approximate derivatives. Lagrange polynomials is another. And then we'll also take a little time to look at how you can use the same idea to approximate the second derivative. In fact, you can kind of see that from these Taylor expansions. Like, what if what if these could be combined in such a way as to get so combined differently? So instead of subtracting them, if you were to add them, well, these terms would cancel out. These terms would cancel out. You get these terms to add together, and then if you subtract off a multiple of f of x naught, then you can get an approximation of the second derivative. So those are going to be very important for solving differential equations. So Okay. Well, got through it. This winged experience. So we'll pick up with this on Wednesday. Okay, I'll stop the recording right here.